okay? You can also use this to discover partial differential equations. So we decided that we would try this on all of the classical PDEs for mathematical physics. So we have our Navier-Stokes data from a code, and I measure velocity and vorticity at points in space and time. And so again, I can compute this big matrix now of partial derivatives, not just of derivatives, but of u sub x's and grad u's and things like that. And again, I'm going to try to find the fewest partial derivatives, nonlinear combinations of these that equals, in this case, the time derivative of my vorticity. Okay, and when you apply this sparse regression algorithm, this is what you discover. This is the system identification model, is the Navier-Stokes equations, and the Reynolds number is within about 1%. Okay, so you can discover PDEs with this basic idea now. And here we just rediscovered Navier-Stokes. We knew Navier-Stokes. But you could also use this to discover coarse-grained models of your PDE from data, from experimental data. People have done that now. A group at Stanford and SLAC is doing this for plasma systems where they don't actually have perfect models. They don't have the Navier-Stokes equations for their kind of non-equilibrium, unsteady MHD, and so they're trying to discover correction terms for their models, closure terms, okay? And since in PDEs we have such a vast amount of spatial temporal data, you can also get away with dramatically downsampling in space and time, and even if you only select a very small subset of the data and do this regression, you still recover the right dynamics, okay? Okay, good. So something else I want to tell you about is this kind of idea. This is the optimization problem we're trying to solve. So Bernd alluded to this earlier, and I want to just really reiterate all of the problems we have in system identification, model reduction, and control theory are optimization problems. And you have to write down the right optimization problem. That's where all the magic happens. That's where all of your human expertise comes in, okay? And our optimization problem is this. So we want a really good fit of our model. We want our model is basically this set of coefficients C, which tells us which terms are active in the dynamics. And I want a really good model fit that agrees very closely with my derivative matrix. But I want as few terms in that C matrix as possible. I want the best fit with the fewest number of terms. So I'm balancing accuracy and complexity. Okay, and this zero norm literally counts how many non-zero elements there are. That's the zero norm. And so this lambda knob, I can make lambda bigger or smaller, and I can promote more complex models or more sparse models. And so this is what that looks like, is you have these kind of complexity and error axes, and you're trying to find the sweet spot in this, and you're going to be sweeping through this lambda parameter to get more complex and less complex models. So I could have a very, very simple model, x dot equals 0, but it has terrible error. That's an underfit model, right? But it is low complexity, high error. I could do a least squares regression. Actually, this is kind of the most obvious thing you would think to do, is don't penalize sparsity at all, just do a least squares regression. That's what DMD would do. And you would get a little bit of activity in all of these coefficients. Least squares spreads out the term so that everybody would have a little bit of activity, and that would minimize your error. So it would actually have the lowest error solution, but we know that that would be overfit to the training data. Okay, I don't believe that a model with 81 terms is the right model, even if it gives me lower error on my training data. And so you hope that there's a family of models between them where you can kind of tune which model you get based on lambda. And you actually hope it looks like this, where there's some sweet spot where you have low complexity and low error. Okay? And you always have to check your system identification model on a holdout data set that you didn't use to train your model. So in machine learning, we call that cross-validation or validation. Okay, and it's as important as a convergent study in numerical CFD. Okay, and when you do the cross-validated error, you'll see very quickly that the least squares solution is in fact overfit. Okay, and so here are the sweet spot where you can get these kind of models that balance complexity and accuracy. So that's what you're trying to do here. Okay, so there's a few things that are particularly challenging. It turns out that the regression problem is easy to solve. That's the easiest part of it. The two things that are difficult are building the right function library. Like, how did I know that polynomials are the right things to use? I mean, I completely cheated because I knew that I was simulating data from the Lorentz system and it was a polynomial. In lots of systems, you generally know what category of physics you're dealing with. Navier-Stokes equations have quadratic nonlinearities, right? We know what our Galerkin projection models look like. They look like linear plus quadratic. So I know that I can build linear plus quadratic models and probably get something reasonable for fluids. If I'm dealing with the nonlinear Schrodinger equation, if I'm dealing with nonlinear optics, I'm going to have a different set of basis functions. I'm going to have, u mod u squareds and things like that. Okay, and so for different physics, you would have guidance on how to build this library in kind of an agnostic way. Okay, so it's hard, but it's not impossible. The thing that's really, really, really hard, how did I know that X, Y, and Z were the right measurements of my system? In the Lorentz system, Lorentz actually handpicked X, Y, and Z. Those were not at all obvious as the right coordinates. The reason he has a paper that is so famous today is because he picked X, Y, and Z. Okay? So the picking of the coordinates is probably the hardest part that no one ever talks about. And it's related to Koopman. It's related to everything we're talking about, and it's very, very hard. And that's where a lot of the best research is going in right now, is how do you find the right coordinate system so that these dynamics become sparse and can be represented easily. Okay, and that's not always obvious at all. Okay, good. A couple of interesting papers. There's an optimization framework to solve this really efficiently now. And there's also lots of other awesome work, in related avenues of parsimonious modeling. Okay, good. Trying to think of what to tell you about next. So there's so much I could tell you about in this. I won't have time to tell you about time delay coordinates, but maybe I'll just tell you very, very briefly now. If I didn't have access to X, Y, and Z, but instead I just had access to, let's say, I just had access to X. This is much more common. Okay, so my wife is a neuroscientist. They put probes into brains and they measure whatever they can pick up. And they're sure as hell not measuring the full state of the system, right? They're measuring a tiny, tiny fraction of the full state of the system, and they're trying to figure out something about the system. Okay, so this is a very, very brief kind of idea of what you can do when you have limited data, but you still want to build a model. So you measure X, you have no idea if it's a good measurement or a bad measurement or sufficient or not sufficient. Okay, you compute X and X dot. And then what you can do is build a Hankel matrix. So you take X at time 1, time 2, time 3, this is your trajectory on the first row. And then you build a second row, which is that trajectory shifted 1 delta t in time. This is a lot like DMD. You shift it 1 delta t in time, then you shift it 2 delta t's, 3 delta t's, q delta t's, and you build this thing called a Hankel matrix. Okay, how many of you have seen Hankel matrices before? So this is actually how classical system identification was done in the 80s. Okay, the eigensystem realization algorithm, the singular spectrum analysis, they did the same thing, but for linear systems. So it's really interesting to take a linear dynamical system and think about what it would look like if you wrote it in this Hankel form. Okay, and that's like 30 years of classic system identification. We're doing it for nonlinear systems like the Lorentz equations now. Okay, so you have this Hankel matrix. You've taken your one-dimensional measurement and you've augmented it into a time delay vector evolving in time. And now what you can do is you can take the SVD of this thing, POD, PCA, whatever you like. They're all the same. So you take the SVD, and now what you have is a matrix U and V. These are eigen time histories. They're eigen time delays in U and eigen time series in V. Okay, we've known since 1980 this Dawkins theorem that says that if you pick the right one-dimensional measurement, like x, that if you build these time delay measurements, you get an attractor that is diffeomorphic to the original attractor. It has kind of the same information in it, but it's a coordinate transformation away. Okay, now here's what's really interesting. We were doing this with a sparse identification of nonlinear dynamics. We were trying to see, could we do this if we only had a measurement of x? So we built this Hankel matrix, we took the SVD, we got these delay coordinates, v1, v2, and v3, and we tried to do SINDI on these coordinates. We tried to build that nonlinear model. And what we found was that every model we tried turned out to be linear, which was completely confusing and very surprising and awesome, because we accidentally discovered that when you time delay your measurement, it linearizes the dynamics. And when it linearizes the dynamics, you should be thinking of Koopman theory. And here's how the Koopman connection works. So K is my Koopman operator. Every column is my previous column advanced one time step in the future. Every column is Koopman times the last column. And so if I have this big matrix and I SVD it, then I can get an invariant subspace to within machine precision so that every column is a linear combination of U, which means every, I have this invariant, this subspace that's invariant to the Koopman operator. I can hit it with Koopman as much as I want, and it's still spanned by the columns of U. That's a Koopman invariant subspace. That's what we were having a hard time finding. And apparently, if you take time delays of your data, you get it for free. Very interesting. We're still trying to figure out the ramifications of this. It works for continuous spectrum problems like the Lorentz system. Very strange. Okay. So that's really just not enough to even remotely kind of tell you about all that there is in system identification. It's getting close to 5, and I realize that tomorrow we're going to talk about fluids, and tonight we're going to drink fluids, and I don't want to delay our drinking of fluids. But I want to just take a step back. There are a few key challenges in system identification. Obviously, discovering F. You could make an assumption about what F is or not, but system identification of F is a big deal. Oftentimes, you're trying to find coordinates where you can get a simple representation of F. So those coordinates could be related to Koopman. You could use DMD to find them. You could use time delays to find them. And there's lots and lots of other considerations. I haven't told you about how you use these for control. That's a huge field. But there's a lot of interesting stuff here, and there is plenty more to do. Lots of good careers waiting in nonlinear system identification. Okay, I'm going to stop there, and I have a couple minutes for questions.
I agree with all your challenges, and I would add another one: how to find your X, your state.
Yeah, absolutely. I mean, that's kind of the whole problem here is what if we measured the wrong thing or didn't measure enough? Building that state X. Time delays is one approach. Neural networks is another approach I'll talk about tomorrow. Not necessarily the best approach, but another approach. Yeah, but finding the coordinates and the right measurements are absolutely vital.
And the next thing is you have to choose X that you don't have false neighbors. So this is the empirical criterion. And the idea of the X is it allows you to integrate into the future. And the X may be too small or too large, or it must have a minimality condition to exclude nearest neighbors.
So this is a really, really good point. Remember our pendulum example? How we were trying to build a minimal state to describe the pendulum, and theta wasn't not enough because I could be passing through this way or this way. If I took theta and theta one time step ago, it is enough because that tells me am I going this way or this way. So theta and a time delay of theta is also a sufficient state of the system. So to some extent, you can get rid of this kind of nearest neighbor confusion by using time delays. Good. Other questions or comments? In the back?
Thanks for a nice talk. This is the first time I heard about Cindy, and I'm kind of, after hearing what it's capable of doing, I'm a little surprised that you haven't presented an example where you accidentally found a reduced order model for something.
Oh, that's tomorrow.
Okay, sorry.
Yeah, so I usually go straight into the fluids application because that's where it shines the most, because the dynamics are polynomial generally. But I decided I would talk about that tomorrow as an example of how you can bake in known conservation laws and symmetries to machine learning models. So I'll talk all about that tomorrow. But you can use this to discover reduced order models. We've done that with Jean-Christophe Loiseau and Berendt and others for fluid systems.
Is it just one other question? Is it dependent, therefore, on your basis functions, on whether or not you do discover a reduced order model or not?
Absolutely. Absolutely. What normally happens is you try different basis functions and it fails. And when you get the right basis function and the right measurements, it just clicks into place and you get a sparse model that's accurate. You definitely know when it works and you know when it doesn't work. Yeah.
Thank you.
Maybe I have a very quick one, a naive question, let's say, on this Hankel matrix formulation. I see you're giving a lot of weight to T1 in this construction. How sensitive does this becomes to T1?
So technically I could shuffle all of the columns of this and it wouldn't change any of the U modes. So that's the weird thing about the SVD, is that I could permute all of the columns and U wouldn't change. Or I could permute all of the rows and V would not change. And so to some weird extent, it's not emphasizing T1 as much as it looks like. So as long as you have, especially in these mixing systems where the more data you collect, the more information you get, you could really start from any time, and just as long as you collect enough data that you've covered the attractor, you're going to be fine.
So, but shall we say that this can only work for a stationary condition? If I have an evolving thing or something that...
Yeah, I don't think this would work for systems that are evolving in time. Or at least we haven't clearly, I'm trying to think if that's true, if we've demonstrated any cases. You know, I actually applied this to the stock market data, to the S&P 500. We were driving through California. This was the summer before Trump was elected. And I applied this to the S&P 500 index and, looking for anomalies. And what I found, I didn't believe, and we didn't include it in the paper, but it would be interesting. You should try it. That's an example of a data set that's non-stationary. It's evolving, and it's, massively forced, and the parameters are always changing. But no, it's not obvious how you would do this on those systems. Sorry? Oh yeah, I can't. So I haven't told you the last part of this, that you can actually get a linear regression model for how these time series evolve. And when you do this, you can model the first R minus one of the eigentime delay coordinates very accurately, but the last one never fits very well. And if you look at this last forcing signature, it's usually almost zero, and then it turns on and becomes active when the trajectory switches to the other lobe. So what we find is that our models have this bursting signal when we have phenomenological switching or bursting. So you can apply this to like disease systems, measles outbreaks. You can basically measure the magnitude of the measles outbreak by the magnitude of this last forcing signature. You can predict when the Earth's magnetic field is going to switch based on the by the magnitude of this forcing signature. So when I was applying this to the S&P 500 stock index, I was looking for major crashes. I subtracted out the mean and and I didn't even subtract out the linear growth. I was looking for spiking signatures as precursors to crashes. And so you could actually find a lot of bursting activity before the last two crashes. Yes?
I've really enjoyed your talk. One scenario would be, in quotation marks, your nightmare. Suppose you have a complex complex system and say one system is a Lorentz attractor, 3 coordinates x, y, z, and the other thing is something like say a Silnikov instability, and then you have one way going from the Silnikov instability to the Lorentz attractor and one from the Lorentz attractor to the Silnikov instability. So now you have the problem that you have some good coordinates for one attractor, some good coordinates on the other attractors, one-dimensional expressways in between them, and I would argue this would be the more generic case for complex systems, and I could give examples for that. So how would you, in quotation marks, partition your state space to find the right local coordinate systems?
It's a really good question. It's one we've actually thought a lot about. So again, not an intro question. What Barent's asking, I believe, is that for most complex systems in reality, you have lots of local attractors and you have switching between these attractors. How would you model that? I would argue that what you really want to do is a hybrid deterministic and probabilistic model. Probabilistic for the switching, deterministic within each basin, and probabilistic for how they bounce between. That's what Frank Noe and Schutte do for their molecular dynamic systems. I think that's what we should be doing for our turbulent systems. A catalog. So probabilistic bouncing around the catalog and then deterministic inside. That's what we're trying, but it's tricky. Okay, it is like well into everyone's afternoon beer time, and I am not going to deprive you of that. So
let's go for a beer then.